Hello, today we're going to talk about code coverage. So to do this, we're going to go through a couple concepts on slides. Then we'll have a couple questions that you can answer. And then you'll even have a chance to try to check this code and its test suite to see what type of coverage that this test is providing on the code. And then you'll get even more slides. All right, so let's get started. So, what is code coverage and why are we looking at this? So, the bigger picture here is that we're looking at trying to find a good way to understand whether our testing efforts are being effective. And the assumption here is that when we're testing, the kind of necessary condition is that we even run the code in the first place. So you often find that a lot of times when there's a problem, you will say like, how did this even work in the first place? Because if you even run it, this code doesn't even work. And surprisingly, that's just the case, is that that code just wasn't even ever run. Maybe it was under a weird condition or just under a path that was never considered. And this is what the goal of white box testing is all about, in the sense of that what you're trying to do is take into account the structure or the internal structure of the code and using that for inferring how much of the code have you run and to use that to guide your testing efforts. And so the benefit of this approach is that your testing criteria is based on the actual coded behavior and not high level requirements, meaning that you're more likely to discover just weird edge cases or things that aren't visible from the high level spec. The other benefit of this is that this is a measure that can be done objectively and automatically, in the sense of that you have um, the ability to, for example, measure and compare two different test suites. So you could say that these 100 tests here are able to achieve 80% coverage of our code, whereas this other test suite is only able to do 40%, right? And so you can use that as a way to say maybe one is better than the other. And so the big picture here is that, or the main takeaway idea is that your goal here is that you're trying to increase the amount of code that can be possibly run just so that we decrease the chances of having a fault. Meaning that you're hoping that if you ran code, you would notice that there's a problem. Now, coverage basically measures this property of how much of the code that you've been running. But the problem here is that there isn't necessarily an easy way to measure coverage that is necessarily effective. So what we're going to be discussing for the rest of this time is kind of all the different strategies that we have for measuring how much code is being run and some of the trade-offs of the different approaches that we can use. So let's start with a really simple piece of code and also the most straightforward approach that we can think of. So this code here, print sum, is really simple. All it does is it takes two integers and it adds them together and then it prints them based on whether it's positive or negative in a different color. So you would think this is a pretty trivial piece of code, but you'll be surprised that there's a lot of nuances to it. So the first approach that we're going to take is statement coverage, which is just taking the number of executed statements and dividing that by the number of statements that there are. So imagine we had a test suite that had one test case where it provided the input of 5 and 10 for the print sum function. So if we were to go through this and actually check to see what its statement coverage is, we could just simply start counting the lines that were run as part of that test. So you could see that we added these numbers. In this case, because it happened to be positive, this became true, and we printed the sum in blue. And we didn't run this part of the code, and then we returned back. And if you were to look in total, there were 7 lines that we could run. And out of 7, the test was able to cover 5 of the lines. So we could say that the coverage or the statement coverage of our test suite is 71%. And if we add in more tests, then we can see that we can increase the amount of coverage we get. So this time we're going to add a new test case that checks for a negative sum. So in this case, a -5 and a -10. And when we add this in, we're going to now be able to take this part of the code. And so coverage is actually summative. So it's going to take all of the test cases and add onto it. And so in this case, we have now covered all the lines and we've achieved 100% coverage of the test suite. So from this point of view, you might think that everything's perfect, that we've done everything that we could to test this code. There's nothing left. But maybe if you take a deeper look at the code, it seems like something might be missing. Maybe this was too easy. And if you kind of look a little bit deeper and you notice the structure of the code, you notice that there's an if, an else if, and an else statement, right? And so there is possibly a case of where you could do none of these actions and just really do nothing. And if your goal was to print out a color, having it print out nothing would be kind of bad, right? And this suggests that already we're finding a simple problem with our simple statement based approach. And so we might need some other way of thinking about this. And so one way to start thinking about it is to use this idea of control flow graphs, which essentially will look at a piece of code, a function, and divide up all the statements and control decisions like if statements and loops, etc., and use that to create like a graph of where's the possible flow of execution. And if we use something like this, then we can start to do some different types of reasoning. So for example, we can take this code in this if statement and say that this is really a decision between going to print something blue or jumping to another decision on to tell if something is red, right? And so given this representation, then what we could start to cover instead of statements are the branches in terms of the decisions that we have. So if we know we have 2 decisions in the statements, then we have 4 branches that we can cover. So when this is true, when this is false, and when this is true, and when this is false, right? So if we were to think about what our existing test suites coverage is in terms of this framework or branch coverage, where we simply take the executed branches and divide that by the number of branches, then we'll find that we are actually only at 75% branch coverage, right? So the thing that was 100% statement coverage, when you look at it from a branch coverage point of view, is incomplete. So you can see that we covered this and this, but not this else, right? So we would need to do something else to be able to add to that. And that's essentially just adding another case that handled when this was 0. And so when this was 0, we would be able to see that we've covered all the possible branches and essentially reveal the fault that was there. So what's interesting about this is when we have more than one test criteria, we start to think about what is the power of each one. And this brings in this idea of subsumption. And so when you cover one given test criteria, say X, you could start to reason that some might implicitly cover another one. And basically what that means is if, in this case, if I cover all my branches, does this also imply that I cover all statements? And in this case, yes. So what that means is if I've achieved 100% branch coverage, then that means I've necessarily achieved 100% statement coverage. And what's interesting about this is that I can gain a lot of mileage out of testing by simply making sure I've hit all the possible branches in my code. right? So if I make sure that I take the true, I have a test that will take a true and a false version of each branch in my code, then I will automatically get 100% statement coverage. So that's pretty powerful and useful, but let's consider another example. So in this case, there's just a really simple if statement and an else, and there's going to be some calculations. And this particular calculation is guarded by a condition or two conditions. So this whole predicate is divided up of this x equals 0, and then an or y is less than 0. So either of these conditions could regulate whether that branch is taken or not. And so again, let's make our representation here. So you can see our control flow graph would look something like this. And I could take this if it's true and take this if it's false. And then I would return. And you'll find that this also achieves 100% branch coverage, given that I have these two test cases, one that will pass in 5 and 5, and one that passes -5, -5. So everything looks great, right? Because we know that this is sort of better than statement coverage, and everything is all possibly covered. There's no more faults to find. Well, all right, so if we look a little bit closer on this line, what again is missing? Well, the problem is that we didn't cover all possible conditions. If you think of it, what ended up happening was our test cases always, even though it did take true and false, it was always happening because y was less than 0, right? Or because this became true or false. This was driving all the behavior. This condition never influenced the decision at all, right? And that's where we get into this idea of condition coverage. So we look at the number of conditions in our code, and this is independent of which branches or which if statements that they're in. And we simply look at whether we made a particular condition both true and false from our tests. And if that is the case, then we'll say it's covered. So if we look back at our code, we'll see that we have only covered one condition, right? We've only covered this case. Now, if we were to change this test case simply to have this x equals 0, all of a sudden our condition coverage would be 100%, because in this case, we would execute, and in this case, we would take this branch true with this condition being true. And then in this case, we would take this branch with this, or sorry, we would still take the true branch with this case, this one, but in this case, this would be false, right? And so in both cases, both x and y have been true or false across all executions. And that means that we got 100% coverage. And what that means is we've had the chance to reveal another fault. In this case, where x was equal to 0, we would get a division by 0 error. So here's a question. If we've achieved 100% condition coverage, does that also imply that we achieved 100% branch coverage, right? Is that true? Does condition coverage subsume branch coverage? Yes or no? All right, so exit out of here. You will have a chance to answer that on your own. And then we're going to take a break before going back into the slides to try to run some code, right? So here is a function. It's not that particularly interesting. That is just given similar to our like print sum. It's given two integers and it's doing some sort of math with it. And returning a value. And here we have a test suite that is using this Mocha, and it's simply just running this function with the input 1 and 1. So what I would like to see you do is to add your own test cases here and keep adding more and more until you can achieve 100% statement and branch coverage. So what this will look like is when I run this npm run coverage tool, what it's running is this NYC tool and its coverage, and it's using its like coverage capability to essentially calculate this out, and then it will generate this report. All right, so if I click here, I could see that right now I have 50% branch coverage and 80% line coverage. So what I'd like to see you do is just to add some more test cases here and see if you can do this. And remember, the key insight here is if you get 100% branch coverage, by default, you should get 100% statement coverage. So you can try to generate test cases that will cover all the branches for this one and of this one, right? And remember, if you're thinking of how many branches I'm going to have, it's always going to be 2 per condition, right? So if I have an if statement, that means there's a true and a false branch. And if I have another if statement, that's another true and false branch. And that's irregardless of how they're arranged. If they're nested or if they're just kind of side by side, they're always going to be just 4 branches. All right, so let's go back to the talk. And here's a chance for you to, yeah, I would pause it and make sure that you've done the other part. But going back to what we talked about is, does condition coverage imply branch coverage? So the answer is no, because as we saw before, you could achieve condition coverage, but not necessarily cover all the branches. And so that's what you saw here, is that we were covering both of these conditions, but we were always being true, right, with this test suite. And so as a result, we got 100% branch coverage, 100% condition coverage, but our branch coverage was only 50%. So the challenge here is to ask ourselves, how is it we can actually cover all branches and conditions together? And so that's where, not surprising, branch and condition coverage comes in. And the idea here is that you take into account kind of a union of branch coverage and conditions coverage together so that you can now have a sense of how many things have you covered. And this sort of looks a little bit different than what we did before, in the sense of that instead of kind of having kind of like that control flow diagram, instead what you're doing here is you're kind of making more of a condition table where you're kind of thinking through what are all the conditions and outcomes I can have, right? So if we walk through the expression that we had, where we had this is equal to 0 or this is less than 0, and we looked at our each variable and the values that we can set, you could say that if we were given 0, then this branch or this condition would be true, and the branch outcome would be true. And if you gave this y this, it would be false, but the branch outcome would still be true. If you gave this false and this 5, this would be false, and the outcome would be false. And if you gave this again, the 5, but this time a -5, you would see that this would be true and the outcome would be true. So in this case, you could see that all of the conditions have been considered true or false, and that the branch outcomes, we have taken both outcomes. But in some ways, these are still a little bit independent, but we know that there's 2 branches to cover and 2 conditions to cover. And so in this case, we covered all of those. And in this case, we would have achieved 100% branch and condition coverage. And if we look back at our subsumption chart, then we'll see that branch and condition coverage would subsume branch coverage as well as condition coverage because it's covering both of them together at the same time. So it turns out that you can sort of do better and to be smarter about it. So there's this idea of multiple condition coverage, which is basically just taking all combinations of a condition in each decision, and then modified condition decision coverage, which is a little bit more intelligent in how it selects the conditions to check, in that it looks for conditions that independently affect the outcome. And if you look at what is this kind of like the industrial standard for the Federal Aviation Administration. So if you're basically on a Boeing jet, what is it that they use for testing their software? Well, that's actually MCDC coverage, right? So any code that goes on an airplane must have 100% MCDC coverage. So maybe that might make you feel better. But this is kind of what they consider, the industry standard for something that is really safety critical. So what's shown a simple example of how this might look like. So I have a really simple if statement that has an and, or has three conditions. Is A equal to true? Is B true? And is C true? So you would only run this code if all three of these things are true. And otherwise, if any of these were false, it would always have an outcome of false, right? And so if you were to think about multiple condition coverage, what we would actually have to do is we would have to go through all permutations of this code of where, this being false, this is false, this is false, this is true, this is true, this is true, and then all the variations of that. And you would actually have to write test cases to cover all those things. And you could do that, but you can also imagine how that can get exponentially difficult the more of these you have in your code. Soon you would be having, exponential amount of things to cover. And so the idea of MCDC coverage is to intelligently filter these conditions so that you don't necessarily have to cover all of them. And the main idea is that you use this insight of not selecting a test case of where you would have never really run that code because there was not a change in the decision outcome. So let me just go ahead and jump to this case of test case 7, where if you were to check false, false, and true with the branch outcome of false, why wouldn't we select this one? Well, that's because if we ran if we ran this code where A was false, we know that this is going to be false. And independent of whether B was true or false, it's still going to be false, right? And so because B does not independently affect the outcome of the test, then we don't select this test case because we already know kind of what the outcome is. And we already have an instance of the same test case that would. So in this case, if this is false, but these are true and true, this is the one that is changing the outcome. If you change this to true, then the whole thing would be true, right? And so what you're kind of seeing here is the ones that get selected involve the variables all independently affecting the outcome. All these jointly must be true for this to be true. This one independently affects the outcome to be false, this one to be false, and this one to be a false. None of the others are selected. And so the kind of theory of the MCDC coverage is it kind of allows you to pick the more important critical conditions that or versions of the condition assignments that you can do that will have an actual effect of whether you take a decision or not. And so if we jump back out and look at our subsumption chart again, you'll see that multiple condition coverage is kind of the highest one. That's basically that full table of all possible conditions. And if you did cover this, then kind of by definition, you also do MCDC coverage, because remember, that's just a smart subset of that. And furthermore, if you did do MCDC coverage, that also does imply branch and condition coverage. Because remember, branch and condition coverage is just jointly taking into account branch and condition coverage, but it actually has no intelligent saying about did I actually check for a condition changing a outcome or not, right? So this is a much weaker form of coverage. All right, well, turns out we're still not even remotely done yet. There's other types of coverage, and I like to kind of point out this high-level landscape here is that there are things like path coverage and mutation coverage and data flow coverage, and only path coverage actually can subsume these existing coverages, versus data flow coverage and mutation coverage are kind of their its own thing, and they don't really fit in this chart with the other ones. But there's kind of one more thing to think about in the sense of, is this something that you would actually want to do in practice? And I would say there's sort of a dividing line here, in that anything below this is something that you could practice in at a company and actually have a realistic test suite that does these things. And mutation coverage is kind of depends on what you're looking for, versus something like path coverage and multiple condition coverage in practice tend to explode or be infeasible to actually fully cover these things. And so that in those senses, they're more of a theoretical criteria. So let's go through with a simple code example, the different ways in which we can see this these different criteria is working. So all I have here is a simple two if statement code block that just checks to see first if x is less than 0, and if it's true, it will do this, and if it's false, it does that. And if kind of this below this if statement, if y is less than 0, it's going to do this, and then it's going to do that. Okay. So what's interesting about this is if you actually think about the different ways you can go through the code. So remember, we had 4 branches, but there's actually more to that. When you think about running through the code, there's actually 4 unique paths that we can run through, right? So if we had a test that went like this, where it kind of ran through and did this, and then another one that ran through and did this, we would actually cover all the branches, right? We would have 100% branch coverage, but we had actually only covered half of the paths that we could do. So what would happen is there's also a path that would look like this, and then another path that would look like this, right? So you could imagine that once you've had several nested if statements, that you can have all sorts of independent paths that you can actually go through. And so when you think of kind of like your start to the exit of a code statement, there's actually much more code paths that you can be exploring. And thus path coverage gives you a good sense of kind of like the ultimate thing that you can cover in terms of control flow. The problem with path coverage is there are lots of cases where this is infeasible. A really simple example is a while loop. So if you had a while loop where you just kept running code until some condition became true, you could potentially have infinitely amount of code paths that you may need to cover, right? And that sort of implies that you could never generate a test suite that would be adequate enough to test all possible code paths that could be there. And it kind of shows like that while path coverage is kind of an interesting concept, to practically get 100% path coverage is probably infeasible. But still, it's useful for reasoning about code control paths in your code and how well you're testing it. So something that's a little bit different is data flow coverage. So what's interesting about data flow coverage is it breaks away from this control flow paradigm and it focuses on assignments and computational uses of variables. So imagine I had this variable A and I wanted to think a little bit more about, well, what are the different ways in which A could be changed, right? And so if I go back to this code diagram and I look at that, I could potentially assign A to X here, and I can also assign A to Y here in this code block. Now I could basically have a code flow diagram that looks like this, and like this, right? So there's all sorts of ways to get at it that I could be running through it, but there's actually only two that really matter for me, which is when the value A assigned by X flows down to here, and when the value A equals Y flows down here. Because what would happen is if this path flew here, this would kill this assignment, and it doesn't matter, right? And so really the only practical flow is this and this, right? And so that there's only two control paths or data flow paths that I would really need to cover for me testing all the different ways in which A can receive a value, right? And so when you look at it from that point of view, you basically are looking at def use chains, which are kind of like data flow paths between basic blocks, and just making sure that you cover those pathways, right? And when you do it that way, it kind of gives you this kind of smaller set of things to check. You're less concerned about all the possible paths, and you're just saying like, hey, look, A can be assigned here or here. Let's just make sure we have a test case that makes that run, right? And so there are tools that can let you do data flow coverage. Data flow coverage is really important, or data flow in general is really important for all sorts of analysis in code and compilers. So under the hood, there's a lot of that going on. But if you just reason about it a little bit more, it helps you think about testing a little bit more effectively. Now, the last one that is a little bit weird compared to all the other testing criteria we have is this idea of mutation coverage. And the main idea of mutation coverage is that instead of thinking of your test and then what's running in the code, you're actually thinking about, well, what if I created an invalid version of my code? And to ask the question of, does my test actually catch that or recognize that, right? And so the way that you would compute mutation coverage is you would do something like this. You would say, well, what happens if I generated a new program such that X was greater than 0? So I changed this to do this, X is greater than 0. And then to look at my test to see if any of them failed, right? So you're assuming that I have a test suite given the current code is passing 100%. Then I generate a mutant, which is a buggy version of the code. And then I ask, do any of my tests catch it? And if that's the case, then we consider that mutant killed or covered. And what you're now looking at is, given all the possible mutants you can generate, how many of them are caught by your test suite? And there are there's a lot of interesting applications for mutation coverage, but at the end of the day, what they're really good at showing is how strong your assertions are at capturing possible deviations from your existing spec. And we'll actually visit mutation coverage as part of our milestone 2. So you'll see more of this come up. All right, so that's it for the slides. And then there's a couple of questions here for you to try answering to see how well that you got some of this material. But should be it. This should be a fun, hands-on way to learn about code coverage and try running some of this. Hopefully you got that 100% there. All right, thanks.